All right, today we're going to talk about 3B, which is looking at the size of numbers and converting things into and out of scientific notation. So first of all, let's just take a second to think about numbers. We hear terms like, this entertainer makes $1 million a year, or this company does $1 billion of business every year, or even our national debt is in the trillions of dollars. And we hear these big numbers so much, sometimes we lose perspective on what they mean. So let's just think a second. Visualize that you have a number line that goes from 0 to 1 billion. It's a big number line. And you wanted to put the number 1 million on it. Where would you put it? A lot of people would think that a million's maybe halfway between 0 and a billion, or maybe even 2/3 of the way. A million's a pretty big number. They think that's going to be pretty close to a billion. Well, actually, 1 million is 1/1000th of a billion. It takes 1,000 millions to get to a billion. So if you were to have your number line, you see it here on the screen, that goes from 0 to 1 billion, 1 million would be approximately where the red line is, almost at 0. It's a very teeny tiny portion. So it's a big difference if someone makes $1 billion a year versus 1 million. These numbers are drastically different numbers. So let's look at a couple of examples just to help us visualize how big these numbers are. Currently, the U.S. national debt is about $17 trillion, and right now, the population of the United States is about 315 million people. Maybe you think it's a good idea to repay all of the national debt, and maybe you want to do that by splitting it up evenly among the United States citizens. Well, if we take that 17 trillion and divide it among the 315 million people to get dollars per person, it would take roughly $53,968.25 per person to pay off the national debt. I don't know about you, but I don't have that much money sitting in a bank account right now. I don't think that it's going to happen that every single person in the United States can come up with that anytime soon. And the national debt's just going up currently. But that's a lot of money. That really puts into perspective what that $17 trillion represents. Another example, let's say that there are 1 billion stars in the galaxy, and you're having trouble sleeping one night, so you decide to count stars at a rate of 1 star per second. You want to know how long would it take you to count all of them in years. And this is a really great problem because it's tying in the unit conversion that we did last week along with the really big numbers that we're talking about today. So start with what you know. You know there's 1 billion stars. And you're counting them at 1 star per second. So per means divide. And because we have 1 billion stars up top, we need to put stars in the bottom so they cancel out. So we're going to write that next conversion fact as 1 second per star so that we have a star up top, star in the bottom, and they cancel. And it might help you on this slide to rewrite it in fraction form to make it a little bit easier to see. So we converted from stars into seconds, but we're trying to get into years. So next we'd convert seconds into minutes. We know that 1 minute has 60 seconds, so we'll put the seconds in the denominator to cancel. And then we'll multiply that times 1 hour is 60 minutes to cancel out the minutes. And then 1 day is 24 hours to cancel out the hours. And then we know that 1 year is 365 days to cancel out the days. So if you wanted to count every single star at a rate of 1 star per second, it would take you 3,170 years. That's a long time. I don't think you're going to make it. So these big numbers are a lot to keep up with, and often we use scientific notation to make it easier. And so we say that a number is expressed in scientific notation if it's written as a number between 1 and 10. It can equal 1, but it's got to be less than 10. So basically it's got to be a single digit number, and it's multiplied by a power of 10. So for example, if we had the number 34,239,000, to put that in scientific notation, we would start at the beginning and we see a 3. So we'll write it as 3.4239. And then we want to count how many places do we have to move that decimal. So currently the decimal, it's not shown, but it's behind that last 0 on the right. Well, if we count how many places we'd have to scooch it over to get to 3.4, that's going to be 7 spots. So we'll write that number as 3.4239 times 10 to the 7 to indicate that we had to move the decimal 7 times. So that positive 7 tells us it's a really big number. And when we write it on paper, we do times 10 to the 7. If you're working in Excel, Excel uses a capital E instead of the times 10. So in Excel, this number would be 3.4239 e to the positive 7 to indicate that this is a big number and the decimal is moved over 7 places. Similarly, we can use scientific notation for teeny tiny numbers. So here we have a number, it's 0.0000428. Very small number. Well, we want to put it in scientific notation, so we need to have a number between 0 and 10, or between 1 and 10. So we've got that 4, so let's start it as 4.28. And then we need to count how many times we moved the decimal. So if we count, this is going to be 1, 2, 3, 4, 5 times. So we're going to write that as 4.28 times 10 to the negative 5. And we're going to have a negative up there to indicate that it's a teeny tiny number. So a positive exponent means it's a big number. A negative exponent means it's small. And again, in Excel, it would be 4.28 capital E to the negative 5 to indicate that we had to scooch that decimal 5 places to the left to indicate that it's a very, very small number. To get numbers out of scientific notation, we just have to count how many times we move the decimal either to the right or the left to make it a big number or a little number. So 1.05 times 10 to the 8, that positive 8 exponent means it's a big number, so we're going to take that decimal and move it to the right 8 spots. So if we move it over, we've got 1.05, it's going to move 1, 2, 3, 4, 5, 6, 7, 8 to get 1.05 times 10 to the 8. Similarly, if we have 8.53 times 10 to the negative 4, we're going to start with our decimal place at the 8.53, and since it's a negative, we need to move our decimal to the left to make it a small number. So we move 1, 2, 3, 4, and then just fill in the zeros. That's how we put numbers in and out of scientific notation. So one example where we can see how handy it is to have scientific notation. Let's say the total length of all the sandy beaches on Earth is about 360,000 kilometers, which is about 220,000 miles. And so that's the length. If we were to kind of stretch all the beaches out in a straight line, that's how long all the beaches would be. And if the average beach is about 50 meters wide and 4 meters deep, we're going to use that fact to figure out how many grains of sand there are. So again, visualize all the beaches on Earth stretched out in one straight long line that's 360,000 kilometers. And then each of those beaches is about 50 meters wide and about 4 meters deep. And then let's say that the grain of sand, just a single grain of sand, it's teeny tiny. Visualize one little bitty piece of sand on the beach is 1 times 10 to the negative 12 cubic meters. So teeny tiny. Visualize moving that decimal spot from the 1 over 12 times to the left. So there's a whole bunch of zeros in the 1. The volume of a grain of sand is very small. Well, if we know how long the beaches are, how wide the beaches are, and how deep the beaches are, we can do length times width times depth to get our total volume. And then we know the volume of a grain of sand, so we can combine those to figure out how many grains of sand there are. So that length of the beach was in kilometers. We need to convert it into meters so that we have the length of the beaches. So we have 360 million meters times 50 meters wide times 4 meters deep, which gives us 72, what is that, trillion? Let's see. Hundreds, millions, billions, yet 72 trillion cubic meters of sand on the beaches. And if we take that total volume and divide it by the volume of a grain of sand, which is 1 times 10 to the negative 12, we can figure out how many grains of sand there are. And if we do that calculation, and I would definitely use Excel or a calculator to do that, we get a huge number. It's 7.2 times 10 to the 22, which is over 1 sextillion. That's a huge number representing all the grains of sand on the Earth.